So let's talk about the diffusion. So previously, in the previous video, we in the convolutional neural network we classify images, and object detection is to locate objects, and segmentation is classify um, every pixel. So now the question becomes: can a neural network create an entirely new image? So for years this was difficult. Um, Earlier image generations had problems like blurry images, unstable training, very slow generation. So researchers searched for another approach. So the inspiration is the physics diffusion. The idea came from thermodynamics. Imagine spraying perfume in a room. So initially it has um, a linear or a straight line of um, perfume. So only one corner has perfume. So after some time, the molecules randomly moves until they're evenly spread. This is called diffusion. Although each molecule moves around randomly, the whole cloud follows a mathematical probability. So researchers wondered if diffusion spreads particles forward. Could we mathematically reverse it? So images are just numbers, unlike gas. Images are simply tensors. Every pixel is just a number. If we gradually corrupt these numbers, perhaps we can also reverse the corruption. That became the idea of diffusion models. So the forward diffusion start with a clean image. So like for example, we have the cat image and add a tiny amount of Gaussian noise, slightly noise cat, and add more noise. So we have the more noisy tensor image. Repeat hundreds or thousands of times, eventually pure random noise, exactly like television static. So what noise is added? Each step adds another tensor. Suppose the image particular having an image noise, and then the image changes slightly. Repeat this many times and eventually the original image disappears. So what is Gaussian noise? The random values come from Gaussian distribution. This means most values are close to zero and only few are large. So each diffusion step only changes the image slightly. So when you reverse the problem, now imagine you only have pure random noise. We can you recover cat image? This is exactly what diffusion models learn. Training. So here's the one of the important parts. So the step one is start with the clean image cat and then choose the random time step. Let's say the time step t is equivalent to 537. So the meaning, apply 537 diffusion steps, and step 3 we generate Gaussian noise, and then step 4 we create the noisy image. Like from cat to forward diffusion is equivalent to noisy cat. Now we feed the model. We input the noisy image and time step. So the output, many of the beginners thinks it will predict the previous image. That's wrong. The model predicts the noise tensor because what we input and is noise. So the model predicts the noise tensor, not the image. So why predict noise? Suppose noise image is equivalent to original image plus noise. The model learns noise. Then mathematically, original is image is equal to noise minus predicted noise. That's why we predict noise, not the image. So we can reverse it, find the value of the predicted noise, or find the value of the original image from the predicted noise. So that's very elegant. Instead of learning what does the cat looks like, the network learns what noise was added. So the model is not trained to predict noise from, like for example, step 536 and 537. Instead, it predicts all the accumulated noise from the original clean image. those time step t. This is extremely important. Suppose original image is cut and we have the 537 diffusion steps. Current noisy image. So that the target is total accumulated noise, not the last tiny noise added. So why? Because every training example is anchored to the original clean image. Instead of learning noise slightly less noisy, noise is slightly less noisy, the network always learns original image to the current noisy image. So total noise. That gives a much stronger learning signal. Let's say in the training example, we have the data set image, which is the time step t, particular time step t, and generate Gaussian noise. You create noisy image with the input noisy image and time step. The target is exact noise tensor. That's one training sample. Repeat millions of times, and the unit gradually learns. And given noisy image time step to predict noise. The lecture, the last lecture we have is like if the model predicts total noise, why not simply do clean image is equivalent to noisy image minus the predicted noise? One step. That seems logical, but it doesn't work well. Why? Because prediction isn't perfect. Suppose true noise is 100 and predicted is 95. So subtracting all at once leaves a larger error. Imagine becomes, or the image becomes blurry. Instead, diffusion removes noise little by little. From noise slightly cleaner, removes the noise again, and slightly cleaner and slightly cleaner until we have the cat image hot cleaner. So hundreds of tiny corrections. Each correction fixes previous mistakes. That's why diffusion produces such highly quality image. Generation pipeline. We start with the pure random noise, then repeat the following. So then from the noise, we have the network called unit, predicts total noise and estimates the clean image. So scheduler computes one small denoising step, slightly clean image, and repeat. Eventually random noise become less and less and then to become beautiful image. So why predict the original image every time? The lecture explains another subtle point. Suppose the model only predicted step 538 and both images are almost entirely random. Example is static to static. That's very difficult. Instead, every prediction is tied back to original clean image. This provides a stable target throughout training. So what about prompts? Original diffusion models work unconditional. Example, we train only bedrooms, so we input the noise and the output is random bedroom. No prompt. Likewise, train only cats, output random cat. The user couldn't control the results. So in the modern diffusion models, researchers later added conditioning. Now training uses noisy image plus time step plus prompt. Example, a puppy riding a skateboard. The prompt is encoded by the text encoder such as clip. The text embeddings guide the unit during noise prediction, and instead of generating any dog, the denoising process is steered toward a puppy riding a skateboard. So here's the complete training pipeline from the data set image to random image, choose random time step. We generate the Gaussian noise, upload the forward diffusion. So we have the noisy image, and this image is fed to the network. And time step T, we have the time step, the prompt, the clip, and embeddings, and fed it in your network. Predict total accumulated noise and compare with true noise, and perform the mean squared error loss, and perform the backpropagation to calculate the gradients, and update the unit parameters. Repeat billions of times until we have the until the networks learn to predict it. So, what about the complete generation pipeline? Let's say we have the prompt, we have the tokenizer, we use the clip text to encode. Now we have the text embeddings, and we here have random noise, and we need to repeat many times. So then we fed into the network or unit and predict total noise. We have the scheduler computes one small delicing step, slightly cleaner image, and repeat gradually, and we will have the final clean latent image. And yeah, that's how we generate image. So to summarize, this is a key takeaways. For diffusion, gradually adds Gaussian noise until that image become random noise, and the unit is trained to predict the total accumulated noise in a noisy image, not the previous image. So during training, the inputs are the noisy image, time step, and for conditioning models, text embeddings, the target, and the true noise tensor. So during generation, the unit predicts the noise repeatedly, and the scheduler uses those predictions to perform many small denoising steps instead of one large jump. And text prompts guide generation by conditioning the unit through the clip text embeddings and steering the noising process towards requested content.